So we've got a model answer video for our reproduction and inheritance test, our key assignment 2. And this is question 7, talking about the ABO blood grouping system. In our spec, we don't need to know a lot about multiple alleles. And indeed, the stuff it's given us here is telling us all that we need to know. We've got alleles determining a person's blood group. Table 1 is the actual alleles themselves. So there's 3 different ones we could possibly have. And then table 2 gives us our genotypes. You've got to remember the key bit of information here is that a person will have 2 copies of this gene, so 2 alleles present. They won't have 1, they won't have 3, they'll have 2 copies. They'll get 1 from the mum and 1 from the dad. Okay, but they've got 2. Which one it is could be any of those 3. And here are some phenotypes, or the characteristics that might be expressed by these alleles. And if A is there, it'll produce antigen A. B there is in the allele, it'll produce B, and poor old O, neither. Here are our, so that's genotypes, and these are our phenotypes expressed as blood groups. And the first question, explain why people with the genotype AB, so IA, IB, have the blood group AB. Right. We might expect from kind of normal Mendelian genetics with Ps and things like that, that one of these might be dominant over the other. So quite often you get just one of these like producing group A or something, but it appears that this blood group AB, a kind of mixture of these two, is formed. And so this, where both are expressed, well, that's codominant. So both IA and IB are co-dominant. You could say they're both dominant, but co-dominant is the word that you should really be using. They're both expressed, and you could actually give us the information from table 1. So both antigens A and B are produced. So it's just using the information there. Explain how meiosis, so we have to give some information about meiosis, results in people with the blood group AB producing 2 different types of gamete with respect to the gene for the ABO blood groups. It sounds like a bit of a mouthful there, but really it's saying, tell us a bit about meiosis, why somebody who's AB could actually produce an A allele and a B allele in different gametes. So you need to think a person who's AB, and it's told us what AB is. So that's the genotype IAIB. So the genotype there is IAIB. And then in meiosis you need to think about, well, this is actually a homologous pair. So one from mom, one from dad, but they're on the same chromosome number. And in meiosis these are going to get segregated, and one's going to go into one gamete, one's going to go into another. So we just need to link that to meiosis. because this is an adult and the gametes are going to have only one copy of that gene. And then which one it is, who knows, that's going to be random for the A's and the B's. So we just need to put that into words. So, and if we think of these as the homologous chromosomes, so here's a chromosome, here's another chromosome. Let's, in this person, let's put some more chromosomes in. But these genes will have a position, and that might be one, and that might be another. So these are on homologous chromosomes these are going to replicate and so on, but they've got a homologous pair. So they are on different chromosomes, but these are a homologous pair of a homologous pair. So these are the homologous pair or the bivalent. These will separate, so these chromosomes will separate in meiosis 1, and which stage of it is going to be anaphase 1. So anaphase 1 of meiosis, and so these are going to separate, and the gamete will only get one copy of these, and in this example they'll only get IA or they'll get IB, so only one allele is in each gamete. So your gametes look like that, and that's meiosis 1, and in particular anaphase 1, where you get that independent assortment and segregation. In one family, the 4 children each have a different blood group. That sounds interesting. Their mother is group A and their father is group B. So for people who've looked at these examples before, this is a classic situation where you've got 4 different children and an A and a B parent. The key bit of information, so they're telling us that the offspring phenotypes, these are the 4 children, the offspring phenotypes are all 4 blood groups, so let's put those in. So we've got A, we've got blood group B, we've got blood group AB, and we've got blood group O. And for these phenotypes, we can think what their genotypes could be. For genotype for blood group A, well, that could be a number of, so going back to our question, they've given this information to us. We've got a choice of things for A, a choice of genotypes for B, so we can't really fill these in. What about AB? Oh, we can only have genotype AB there, and actually for O we can only have that genotype for O, so we're just going to transfer those from the table. So the genotypes, and I'm going to put commas here to separate them. AB can only be AB, and the O can only be IO. It's soft to work with. No. There we are. And these could be a number of different things, but one common thing, they're going to have their A, and it's not going to be a B in the other one. So that one's going to have an A, and that one's going to have a B. Okay. What the other one is, well, could it be a B? No, because that would give blood group AB. Could this be an A? Oh no, that would give AB again. Are there any other options? No. So this must be O. So those genotypes for the children give those blood groups. They could be here, they could be AA. But now we need to go, why can't it be AA there? Well, the answer is we get one of these from mom, one of these from dad. So the parents here, blood group A, so the parental genotypes, it's going to be A there, and that's going to be B there. Well, can this parent give an A over here? Well, if we take this back to here, this solves our problem for us. These O's must have come from somewhere. We must have got an O from each parent, which just answers our question really easily. And then the rest of that just fits in. So for the first child, we've got A and O from the other parent. This child, we've got our O and B coming from two different parents, that figures. And this child, we've got A and B coming from each one, that's possible, and we've got two O. So these are all now possible. And the gametes here, these are going to be easy enough. I'm just going to make these nice and separate to show that they are separate. And you just copy them down from there. And that all fits in nicely now. But if you've seen that question before or in textbooks, then you know that answer anyway. We've got some data, 120 children, and they've actually, using the cross that we've just done, they've got some data on blood groups. And I'm going to use a chi-squared test, but it tells us the ratio that we'd expect. And actually from this cross here, yeah, this ratio of 1 to 1 to 1 to 1 is the most likely using those. That's what we'd expect, certainly, if we drew a Punnett square there. But have we got a 1 to 1 to 1 to 1 ratio? No. Okay, what would we expect? If there's 120 and we're dividing it into 4 equal groups, then we just need to calculate that. So 120 divided by 4 is 30. So we'd expect these to be 30. So this is what we observed. What would we expect? We'd expect 30 in each of those. And that would add up to 120. And the chi-squared test is going to see whether these 26 and 31 are significantly different from our expected 30. So they've put a really nice table in for us to get it all organised, which is really good. So we can put our 30s in. There we are, and just follow the rules. O minus E, so 26 minus 30. 26 minus 30, that's minus 4. 31 minus 30 is 1. 39 minus 30 is 9, and I know you can do those without using a calculator. So the best thing to do is do it in your head, get a number, and then just put it in your calculator anyway. You've got two given the same number, it's probably right. 24 minus 30 equals minus 6. And if you get the minuses wrong around, it's not the end of the world, because we are now squaring these. And if you square two minus numbers, it will give a positive number, or square two positive numbers, it will give a positive number as well. So this step is designed to get rid of any of these minuses. So square minus 4 times by minus 4 is going to give you plus 16. Let's see if we can prove this on this calculator. So 4, that's a minus 4, times by minus 4 is 16. So that works as well. 1 times 1 is 1. 9 times 9, if you remember your 9 times table, is 81. 9 times 9, 81. And minus 6 times minus 6, well, 6 times 7, 6 sixes are 36. Okay, we'll do that. Then we're going to take this and divide it by e. So we'll definitely need a calculator for this bit. So 16 divided by e. 16 divided by 30. 16 divided by 30, 0.53. Now I'm just going to use 2 decimal places here. If the answer's really, really close later on, I might have to come back and put more decimal places in. But look how much space they're given us, so I'm just going to use 2 decimal places. That's sensible. And then we've got 1 divided by 30, which is 0.03. 81 divided by 30 is 2.7. And 36 divided by 30 is 1.2. Even though it says 1.2, I'm going to put 1.20 in because I like things nice and tidy like that. And then this step here is add them all up. So we're going to add all of these up. So here we go. 0.53 plus 0.03 plus 2.7 plus 1.2 equals 4.46. So this is our value for chi-squared. So that number is our value for chi-squared. We've calculated chi-squared, because chi-squared equals the original equation is that. And we've got a critical value. So now we've got chi-squared is a number, and we've got a critical value, which is another number. And 3 degrees of freedom. Well, the 3 degrees of freedom is calculated from how many groups have you got minus 1. So 4 minus 1 is 3. Okay, so our degrees of freedom is going to be 3. 0.05 probability. Well, we'd like to be absolutely certain, but in biology, nothing is absolutely certain. So about a 1 in 20 chance is good enough for us.
No, I'm pretty certain.
Miss Knights is more certain than the rest of us about many things.
And if I was getting on the plane, I'd want to be really certain.
Yeah, that's right. I was taking some drugs. So, but this 1 in 20 or 95% certainty, or in strict probability terms 0.05, is okay. And this gives us a critical value of 7.82. So what we're doing now is we're comparing our chi-squared number with our critical value. And I always remember it one way. There's a few different ways to remember this. We've got a null hypothesis. A null hypothesis is that there's no difference between these two sets of data. There's no difference between the expected and the observed. Any differences are just down to chance. And if our chi-squared value is above our critical value, then we can reject our null hypothesis, and say something's going on. They're too different. On this occasion, our chi-squared value is not bigger than our critical value, so we must accept our null hypothesis that any differences between these is purely down to chance. So we can say our results are down to chance. You know, the probability is less than our 5%, or we're 95% certain. Okay. Our chi-squared value is less than the critical value, and so we must accept our null hypothesis that any differences between these are purely down to chance. Hope you enjoyed that. See you for the next question.